Hi, my name is Noson Yanofsky. We're doing classes Discrete Structures. We're going through the homework, the answers to the homeworks for Chapter 5. So we did Section 5.1, 5.2, 5.3, and we go through the homeworks fairly quickly. I'm not going to give you the exact numbers. I'm going to show you how to set up the problems and do it. It should be totally understandable. Now, I just want to warn you one thing. Do not watch this video if you haven't worked out the problems yourself. If you're just going to read through this, watch this and say, oh yeah, I would have done that, I would have done that, it's worthless. Okay, so then just shut the video and go play a computer game or watch a movie or something like that. The whole thing is to get you to do it. If you're stuck and you thought about it for a long time, try another problem, come back to that problem that you're stuck on. But the goal here is to get you to understand how to do this on your own. Okay? So don't just watch me to do it. This is just a quick way of doing these things quickly. Okay, so let's go through it. 1E, so we're going to do this a little bit quickly. 1E is 52, choose 52. Well, that's equal to 1. It's pretty easy. 1F, this is 52, choose 1, which is 52. Okay, so that's pretty easy. Next. Okay. 3C is P of 10, comma, negative 2 plus P of 10, comma, 17. How could you have 10 objects and choose 2 of them in order, or negative 2 of them in order? It doesn't make sense, so that's a 0. How could you have 10 objects and choose 17 of them? You can't. There's no way of doing that, so you do that 0. So that's 0. Just put these in to show you these are the other things. Okay, 3E. Okay, so you'll look at the problem, but the answer is 1000 factorial divided by 999 factorial times 649 factorial divided by 650 factorial. Now, 1000 factorial is basically 1000 times 999 factorial. So that becomes 1000. These two cancel out, and you're left with just 1000 on top. And on these two cancel out, and basically you're left with 650 on the bottom, which is equal to 1.5384. Great. 5A. Given 20 types of inputs to a program, in how many ways can 8 of them be selected? Okay, and the answer is 20, choose 8. Okay, and you can figure this out. You have to multiply it out, but a lot of them go out, and you get 1, 2, 5, 9, 7, 0. Okay, 5B is as follows. Let's just read the question. If order matters, okay, so that is P of 20, comma 8. Here we divide it out by the order. Here we didn't divide out by the order, okay, and so we get 5079110 Great. 7A. How many committees consisting of 4 people can be chosen from 9 people? 7A is 9, choose 4. Okay, you're gonna figure out that's 126. Okay, I'm not gonna put down the numbers anymore. You're gonna have to calculate the numbers. I'm gonna give you the choosing, but you're gonna have to calculate the numbers. Okay, let's just make sure you can see this. Good. 7B. Let's read the question. How many committee members consisting of 4 people can be chosen from 9 people? Redo part A if there are 2 people, Ann and Bob, who will not serve in the same committee. Okay, so again, you have 9 choose 4 ways of doing things, but then you have 2 people that don't want to be in the same committee. So here's a way of doing it. Again, the word don't is do not. hear the word not, you mean there has to be a minus there. So the way to do it is, look, how many committees can I make with Ann and Bob in it? Okay, and then I'm going to subtract those. Well, if I have Ann and Bob in the committee, then I only have 7 people left, and I want to choose 2 more. So it's 7 choose 2. So again, these are all the committees. These are the bad committees that have Ann and Bob in them. How many are there? Well, you have 7 other people, and you want to choose 2 more to make a committee of 4 people. So that's that. Okay, anyways, that's 105. Okay, number 9. Let's erase. Let's erase. Number 9 is as follows. You have 9. You have T has 7 people, 7 elements. S has 4 elements. Okay. A is as follows. And how many one-to-one functions are from T to S? Okay, and the answer is P of 4, 7. Okay. How many one-to-one functions are from T to S? Answer: there is none, because there's no way you're going to have T different elements going to 7 different elements going to 4 different elements. No way. So this is equal to 0. Okay. As opposed to that, number B is how many one-to-one functions from 7 to 4. So this is from 4 to 7. So this is 7. Seven comma 4, and that's 840. Okay, and C, here we're not interested in one-to-one functions, so we can have repetition. Okay, and that is equal to 7 to the 4, which is equal to 2,401. Great. Number 11. Let's read it. Cards are drawn from a deck of 52 cards with replacement. That means you're pulling out the cards. Okay? In how many ways can 10 cards be drawn so that the 10th card is not a repetition? Okay? Okay? And so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? You have 10 cards. Okay? And you want, what do you want? Let's just read that again. Cards are drawn from a deck with replacement. That means you take out one, you put it back. You take out one, you put it back. You take out one, you put it back. So you have 52 possibilities for this, 52 possibilities for this, 52 possibilities for this, 52 possibilities for this, etc., etc. Okay. But the last one, it says as follows. In how many ways can 10 cards be drawn so that the 10th card is not a repetition? That means whatever cards you chose here, ooh, made a mistake. Because I could have chosen the same cards. Okay. Anyways, I think it's 43, but I probably made a mistake here. Okay. Great. In how many ways can 10 cards be drawn so that the 10th card is a repetition? So I think that is 52, 52, the same thing, 52, and then you have a 9 here. I think I'm wrong there. Great. Number 13. Let S be the set of 7-digit numbers. Okay, find S. You know what, I'm just going to write the answers so you don't have... Okay. Let's read the questions. 13. Let S be the set of 7-digit numbers. Find the number of elements in set S. Okay, this can't be a 0. All the rest can be anything, any other digits. So it's 9 times 10 times 10 times 10, etc., etc. Okay? Number B, how many members of S are even? So again, this can't be a 0. This can be anything. There are only 5 digits here that are even. 2, 4, 6, 8, and 0. Okay, so that's that. We'll multiply that out. How many are, I'm sorry, that's how many are odd. So this is how many are odd. So 1, 3, 5, 7, and 9. This is, number C is how many are even. How many are multiples of 5? A multiple of 5 is going to end in either a 0 or a 5. 5, 10, 15, 20, 25, 30. So you only have 2 possibilities for this last digit. So that gives you that. Okay, the rest is the same. Next, E. How many have no 2 digits the same? Again, this has to be a 9. There's 9 possibilities for the first. You cannot have a 0 here. Okay, now this one can be anything but what this was. He could be a 0, but he can't be what this is. So he also has 9 possibilities. He has 8 possibilities, 7 possibilities, 6 possibilities, 5 possibilities, 4 possibilities. So it's 9 times 9 permutations of 9, 6. Great. F. How many odd members of S have no 2 digits the same? So it's the same thing as before, F. How many odd number of S, so that we did that, have no 2 digits the same? So it's again, well, F. Okay, well, you have 5 odd digits here, okay, but each one, this could be, well, I don't know why I did this. Oh, because, right, so this guy, so let's say this is a 3. 3 is an odd digit. So this guy cannot be a 0, and he can't be a 3. This guy can also not be a 0, and he can't be a 3. He can be a 0, but he can't be a 3, and he can't be what this is. That's why he's 8. Okay? He can't be what these 2 guys are, but he also can't be this 3. Okay? So we have this over and over, and that's only just for the 3 who's odd. But what about for the 1 who's odd, for the 5 who's odd, for the 7 who's odd, and for the 9 who's odd? So we have to have 5 of these. Okay, great. I could have just put the 5 over there, but it's a little bit more harder to explain. How many even, this is G, how many even members of S have no 2 digits the same? Okay, so, I don't remember why I wrote that. Hold on. Okay, this could be a 0. Ah, right. Okay, this could be a 0. This anyways can't be a 0. So this is going to be 9. So you have no 2 digits the same. So this is a 0. This can't be a 0, but it can be any of the other digits. Okay, he can be anything except this. So we have like that. As opposed to that, let's say he's a 2. This is even numbers, so he's a 2. Okay, so he can't be a 0. Why can't? But he can't be a 2 either. So he can't be 0 and he can't be 2. Okay, so that's why he's 8. He can be 0. He can't be whatever number this was, but he can't be a 2 because that's this. Okay, so you have, and this is true. So this is true. This is the 0, and this is true for 2, 4, 6, and 8. And so that's why you have 4 of these. Okay, great. 15A. Okay, I'm going to go through this a little bit quickly. 4 of a kind. What that means, okay, on the page it tells you what 4 of a kind means. 4 of a kind means 4 cards in the hand have the same value. Okay, so what's the value? There's 13 possible values. So it's 4 aces, 4 deuces, 4 threes, 4 fours, 4 fives, etc. There are 13 possibilities. Now, you have to worry about the other cards also. So there's 48 other cards that you have to choose. It's 5 card poker, so you have to choose 4 cards and then 1 more. Okay, next, 15b, a flush, but not a straight or a royal flush. Again, you'll have to look up what these means, but basically you have, whoops, left out parentheses. Okay, this is subtracting the royal flushes. I'm sorry, the straights. So you have 4 different suits. You have to choose, of the 13 cards in that suit, so you have to choose 5, but you don't want them in order. Okay. Now, if you think how many orders there are, you can have 1, 2. I'm going to forget, not call them Mason deuce. 1, 2, 3, 4, 5, or you can have 2, 3, 4, 5, 6, or 3, 4, 5, 6, 7. You can go all the way on, but you have to realize you can't go past 10. No, 9. 9, 10, 11, 12, 13. Right? Jack, queen, queen, 13. So you have 10 of those possibilities. Okay? And finally, this one is as follows. Well, you'll figure this one out by yourself. So you have 3 of one type. 13 cards, you have 3 of one type, and you have to worry about 2 more cards. And the 2 more cards, you have 12 possibilities for the 2 more cards, you have to choose 2, but you have 2 other suits that you have to choose for those 2 cards. So that's section 5.1. Let's do section 5.2. Okay, this is the homework for section 5.2, and like I said, this is all probability, but like I said, probability is basically just 2 counting problems. You count what's on the top, you count what's on the bottom. You count what you want to happen, you won't count what could happen. That's the bottom. Okay, so let's go through it. An integer in 1 through 25 is selected at random. What is the probability that the number is divisible by 3? Okay, anyways, so think about it. 3, 6, 9, 12, 15, 18, 21, 24 is divisible by 3. So there's 8 of them. Okay, divisible by 5, 5, 10, 15, 20, 25. So that's 5 over 25. So again, you're randomly picking something. What's the chances of how many different things can happen? 25 things, but you want 5 of those. Number C, prime. Let's go through it. Well, 2, 3, I'm not going to go through it. There are 9 prime numbers. Let's do it. 2, 3, 5, 7, not 8, not 9, not 10, not 11, not 12, not 13, not 14, not 15, not 16, not 17, not 18, not 19, 19 is prime, not 20, not 21, not 22, not 20, 23 is prime, 23, 24 is not prime, 25 is not prime. Okay, great. 3a, 4-letter word is selected at random for sigma 4. So you have 5 letters, 5 to the 4 possibilities of what you're doing. So there are 5 to the 4 words possible. Okay, so that's always, we're always going to have 5 to the 4. Okay, but now let's see. What are the probabilities that the letters in the word are distinct? Well, if you choose one letter, then the next one can't be it, and the next one can't be that either of these two, and so you have that. Okay? And again, you're going to have to figure out the number. On a test, you have to give me the number. You can't give it to me like this. But that's easy. Okay? Now, B. What are the probability that there are no vowels in the word? Well, the letters are A, B, C, D, E. A and E are vowels, so you have B, C, and D. The only thing you have is B, C, and D. So there's 3 non-vowels. So you have, and they're 4-letter words, so you have that. Okay? By the way, this is 3 over 4. Well, anyways, this is 3 over 5 to the 4th power. Doesn't matter. Okay? Number C. What is the probability that the word begins with a vowel? There are 2 vowels, A times E. The other 3 things can be anything else. Any other letter, including A and E. So you have that. So that's 2 over 5. And by the way, you don't have to do the whole thing. Just think about it. I'm not looking at the whole word. I'm just looking at the beginning of the word. The first letter in the beginning of the word is A, B, C, D, or E. Two of those are vowels, so it's 2 out of 5. You don't have to look at the rest of the thing, so it's 2 out of 5. Okay. Next, 5. An urn contains 3 red balls and 4 black balls. Okay, there's a lot of things like this. A set of 3 balls is removed at random from the urn without replacement. Give the probability that 3 balls are all red. Well, you have 3 red balls. You want to choose all 3 are red. You want to choose all 3 of them. 7 choose 3 is going to be the answer to the bottom of all the answers because you have 7 balls in the urn altogether. You're choosing 3 of them. So look what it says. This is 3 red, and I want to choose 3 red. Okay, let's do the next one. 4. All black. Well, there are 4 possible. By the way, this is a 1 on top. There are 4 possible black. There are 4 black balls. You want to choose 3 of them. So that's 4 choose 3. 4 choose 3 is, by the way, 4. Okay. Next, number C. You want 1 red, so you have 3 possible reds. You want to choose 1 of them, and you have 4 blacks. You want to choose 2 because you have 3 altogether. So you can have 1 plus 2 is 3. So that's that. Okay. Next possibility, D. 2 red, so you have 3 red altogether. You want to choose 2 of them, and you have 4 blacks. You want to choose 1 of them. So you're going to get it like that. Okay. And 5. Sum the answers from part A to D. Well, look what happens. You reach in, you're going to pull out sum. What are the possibilities? How many red possibilities will you have? You could choose 3 reds. You could choose no reds. You could choose 1 red. You could choose 2 reds. So 0, 1, 2, 3 reds. That's it. So those are all the possibilities. Conclusion, if you add up all these numbers, and you should actually do it, you get a sum of 1. Okay, great. Next, we do all the even ones. 7. Okay, the 7 we're going to have to write. Okay. 7 says as follows. You have an experiment that leads to events A, B, and C with the following probability. Notice there's a mistake there because C is not used at all. Probability of A is 0.5, probability of B is 0.8, and probability of A intersect B is 0.4. Okay? Find P of B complement. P of B complement is those things not in B. Whenever you see not, you mean minus. So it's 1 minus P of B. P of B is 0.8, so 1 minus 0.8 is 0.2. Okay? B is A union B, and here we use the inclusion-exclusion rule. Here we use that rule that we saw. So basically it's 0.5 plus 0.8 is 1.3, minus 0.4 is 0.9. Okay, so it's this plus this minus this is equal to 1.9. Okay, this is the clever one. Let's read it. P of A complement union B complement. Now, the way to do this is to realize that we can use De Morgan's law. You remember De Morgan's law? We did it the first week of class. So this is A intersect B complement. Okay? Remember this? If you're not a female or not a Democrat, okay, that means you're a male and you're not a male and a Republican. I'm sorry. Let's do that again. If you're not a female or not a Democrat, that means you are not a female and Democrat. Okay, anyways, De Morgan's law, that's De Morgan's law. Now, once you have the word complement, complement means those things not in it, so you're going to have a 1 minus. 1 minus those things in A intersect B. But we saw that A intersect B is 0.4. We were actually given that, so it's 1 minus 0.4. 1 minus 0.4 is 0.6. Great. Number 9 is a review of that 5-card poker game. But here we're doing it with probabilities. Okay, it goes as follows. A 5-card poker hand is dealt. Find the probability of getting 4 of a kind. So what does it mean 4 of a kind? You have 4 aces, 4 deuces, 4 threes, 4 fours, 4 fives. So there are 13 possible things that you can have 4 of, and then you have to pick a 5th card. There are 48 other cards to pick. Okay, each one of these are 52 choose 5 on the bottom. Okay, each one of these 52 choose 5. Okay, next, B. 9B. 3 of a kind. That means you have 13 possible cards. There are 4 suits. You have to choose 3 of those suits. Okay, and so that takes care of that. But you have to pick 2 other cards. So you have 12 other numbers that you can pick. You have to pick 2 of them, and you have 2 other suits that you can choose. Now, 3 of a kind means that you don't have 2 of a kind also. So these has to be different. Okay. Last one, C. A non-exotic straight. Actually, I don't do D&E. A non-exotic straight. So that means straights. That means one number after another. Okay, but we don't care about them matching the suits matching. So 4 to the 5th. Okay, you have 5 cards, 4 different suits. Okay. Straights, well, they can all start at 1, they can start at 2, they can start at 3, they can go all the way till 9 or 10, something like that. So that's how you get the straights. Minus, you don't want them to be in the same, suit. So there are 10 times 40 of those in the same suits. Okay, great. Let's do number 11. Okay, number 11 has a lot of writing. I don't want to write it out. Okay, so let's just talk it out. Number 11A. Okay, let's read it. A black die and a red die. So each die, you roll it. It's going to get either. It's going to either be 1, 2, 3, 4, 5, or 6. But you have 2 die, and the point is you can tell them apart. You can do the same exercise, it's a good test question, if they're both dies are the same color and you can't tell them apart. Okay, but you have a black die and a red die are tossed as an example 5. What is the probability, you read the examples, what is the probability that the sum of the values is even? The main point is, the bottom is 36, because you have 6 possibilities for the red die, you have 6 possibilities for the black die. Okay, now, what the sum of the values is even. Now I'm going to give you 2 ways of doing this. Now look, the sum of the values are even or odd, so it's basically 50-50. And what else could it be? Okay, but that's a little bit, it could be that there's some way of getting more than that. Okay, but the right way of doing it is actually sit down and write down all possibilities. 1 plus 1 is even, 1 plus 3 is even, 1 plus 5 is even, 2 plus 2 is even, 2 plus 4 is even. And I wrote down all the possibilities, and you get 18 possibilities of getting an even number. So you have to add the evens with the evens, the odds with the odds, they give you evens. Okay? Number 11B. The sum on the red die is bigger than the sum on the black die. Again, there's no quick way of doing this, you just have to do. The red die is 2, the black die is 1. 3 and 1, 4 and 1, 5 and 1, 6 and 1. 3 and 2, 4 and 2, 5 and 2, 6 and 2. All the times, the one die is larger than the next die. Okay? 4, 3, 5, 3, 6, 3, 5, 4, 6, 4, 6, 5. Okay? Anyways, there are 15. Over 36 possibilities for that. Okay, number C, 11C. The number on the red die is twice the number on the black die. Well, there's only 3 ways that can happen. The red die can be 1, the black die can be 2, or the other way around. This could be a 2, and this can be a 4. This can be a 3, and this can be a 6. Okay, the smaller ones are, that's the only possibilities you can have, so that's 3 over 36. Those are the probabilities. Great. Okay, number 13. Okay. Number 13 just tells you to prove the result about the inclusion and exclusion, but we saw that result. It's the beginning of chapter section 5.3. So it's just proving things with the inclusion and exclusion. In other words, if you have 3 possible events, you want to count the number of elements in all 3 of those possible events, you have to do that 3-part Venn diagram, and again you have to do it. So we're going to leave it because it's not hard. Number 15. Let's erase. Okay, this is kind of an important one. So let's do it in all its name. A fair coin is tossed 6 times. Find the probability of no heads. Okay? Okay, so how many different ways are there of flipping a coin 6 times? Okay, and the answer is 2 to the 6. I know 2 to the 6 is 64, but I just want to leave it as 2 to the 6 so we can see it. Great. How many ways are there of getting no heads? Well, there's only one way of getting no heads, namely all of them are tails. That's pretty simple. B. How many ways are there of getting 1 heads? Okay, I don't want to write this as 1. I want to write this, sorry, I don't want to write this as 1. I want to write it as 6 choose 0. I have 6 of the possible flips. I want to know how many of them can be 0 of them should be heads, and that's 0. That's 1. That's 1. There's only 1 possibility. Okay. B. How many of them are 1 heads? Well, there's 2 to the 6 things that could happen, and you want 1 of them. So there are 6 possible flips. I want to choose 1. Well, there are 6. Either the first one is a heads, or the second one is a heads, or the third one is a heads, or the 4th one, or the 5th one, or the 6th one is a head. Okay? 2 heads. You guessed it. 6 choose 2 over 2 to the 6. I think that's 15. Okay? 3 heads. 6 choose 3 over 2 to the 6. Okay? Finally, more than 3 heads. Well, how many heads could you have? So this is E. More than 3 heads. Well, what could I have? I could have 4 heads, or is plus, 5 heads, or 6 heads. That's pretty simple. Okay. Okay. 17, I cheat a little. I don't really want to get into it. The thing is, you flip a coin n times. Okay, you flip a coin n times. So the question is, a fair coin is tossed n times. Show that the probability of getting an even number of heads is half. Okay. I don't want to do proofs. People don't like proofs, but besides the fact, there are 2 to the n possibilities. When you flip a coin n times, you get 2 to the n possibilities. Okay? The chance of getting an even number is 2 to the n minus 1. Okay? And that's equal to 1 over 2. Okay? Okay, great. Let's do number 19. Number 19. Okay? A set of 4 elements is selected. I don't think I assigned 19. I think I did from 1 to 17, but we'll do it. A set of 4 numbers is selected at random from the set 1 through 8 without replacement. That means you just pull in and you pull out. What is the probability of exactly 2 are even? Exactly 2 are even. So, let's go through this. 19A. Let's see. In each one, you have 8 numbers. You're choosing 4 of them. That's how many things can happen. Okay? But here, you want 2 of them to be even, exactly 2, and 2 of them could be odd. So there are 4 odd numbers. You want 2 of them odd. Okay? B. 19B. None of them is even. Okay? So that is 4 choose 4. All of the odd ones I want to choose. By the way, there's only one way to do that. Of 8 choose 4. C. Exactly one of them is even. So let's do this. 4, 1 is even. 3 of them are odd. 8 choose 4. D. Okay? You have to worry about every single thing. So if you just says one of them is even, you have to worry. You want to know how many different ways that they are choosing the other. What are the other ones you're choosing? What are the odd ones you're choosing? Okay? Exactly 3. So we did D. Okay. D is exactly 3 of them are even. So that's, I have 4 even, I'm choosing 3 of them. I have 4 odd, I'm choosing 1 of them. I have 8 choose 4 altogether. E. Okay. E is all of them are even. So that's 4 choose 4, which is 1. There's only one way to choose all 4 of them, and there's 8 choose 4 ways of doing that. Okay, so that is the end of section 4.5.2, and now I want to do section 5.3. I'm going to erase stuff. Let's erase. Okay, so now we're doing section 5.3. We're doing the homework questions for section 5.3. Okay. This is actually cute because we have a little mistake here. Number 1, among 200 people, 150 either swim or jog or both. If 85 swim and 60 swim and jog, how many jog? So you have 150 swim or jog, that's 150. 85 swim, 60 swim and jog, that's intersection, those are the people that swim and jog. Okay, I put it into this inclusion-exclusion, so we have this X we don't know. This is what we're asking, how many jog? And if you do 150 minus 85 minus 60, you get 125, I'm sorry, plus 60. 150 minus 85 plus 60 is 125. Great. Next, number 3. An integer is selected at random from 1 through 1,000. Okay, what is the probability that's divisible by 7? Okay, so take 1,000, we did this in class, take 1,000 divided by 7, you get 142 point something something, okay? 142 is the floor of that, so you get 142. Next, okay, again, every single experiment here is you're reaching in and you're grabbing 1 out of 1,000. There are 1,000 possibilities of how that can happen. B, divisible by 11. So again, here's what you do, 1,000 by 11, okay, take the floor of that is 90. So it's 90 over 100. Okay, this is the hard one. You ready? Not divisible by 7 or 11. So divisible by 7 or 11, not complement. Okay, so how do we do that? Well, complement, you do 1 minus. Complement is not, so you do the minus. 1 minus divisible by 7 or divisible by 11. That's what the complement is. So notice here this is C, here's no C. Great. Question, how do you figure out how much is in 7 union divisible by 11? Well, this is the whole inclusion-exclusion thing. So it goes as follows. 1 minus divisible by 7 plus divisible by 11 minus divisible by 7 and 11. Okay, so divisible by 7, we figured that out already. Divisible by 11, we figured that out already. How about divisible by 7 and divisible by 11? If you're divisible by 7 and you're divisible by 11, then you're divisible by 77. 7 times 11. You're going to have 7 and 11 as a factor there, so you're going to have 77. Take 1,000 divided by 77, you get 12 point something. Okay, so you get this. Now do 1 minus this plus this, you can figure it out. Last one, we didn't finish it. Number D, 7D. I'm sorry, 3D. Divisible by 7 or 11, but not both. So we didn't have this yet, but let's do it. let's say I wanted to know, we had this called the symmetric difference. I have a set A and I have a set B. I want those things in A or B, but not both. So that means these guys. Okay. Okay. So we can do it as follows. A plus B, that's the symbol we used, is equal to those things in A plus those things in B. But 1 second. That is this twice. I don't want this twice. I don't want to count these guys. So simply, minus 2 times A intersect B. Not, that's the regular thing. That's for the union. But now I want to take off 2 of them. Okay, so that's done like that way. Okay, now we can use the same thing for part D of number 3. Probability of divisible by 7, or, I'm going to write or as plus, symmetric difference, or divisible by 11, but not both. Okay? And so that's equal to probability divisible by 7 plus probability divisible by 11 minus 2 times probability divisible by 77. And we have those numbers, you can plug them in. Okay? So again, this is those things in A plus those things in B, not those things, minus 2 times those things there, because we added them twice. Okay, great. So this is 3D. Great. Let's go on. Okay? Number 5, I'm going to leave for you, because it's a triple thing. It's the same idea, but it's probability of divisible, I'm just going to set it up, by 4, union, divisible by 5, union, divisible by 6. Okay? Now, that's a 3-way inclusion-exclusion. It's not hard, I just don't want to do it because it's just a lot of time. Okay, great. Number 7. Okay, here's that putting in identical things into different boxes. So we're going to see these problems a lot. Number 7. Let's read it. 12 identical letters are to be placed in 4 mailboxes. In how many ways can this be done? Okay, so you have 12 things and you want to put them into 4 mailboxes. Okay, and we saw how to do this. Notice you need 3 boundaries. So this becomes 12 plus 4 minus 1, okay, divided by 4 minus 1. Okay, and you can figure out what that number is. This is part A. Part B is more interesting. Part B. How many ways are possible if each mailbox must receive at least 2 letters? Okay, so I'm going to put 2 here, I'm going to put 2 here, I'm going to put 2 here, I'm going to put 2 here. So altogether I have 2, 4, 6, 8, I have 8. So I start off with 12, but then I get 4 left. And now, all I have to do is, where do I put these other 4? I have 4 possibilities for each one of them. And so it becomes as follows. 4 plus, I'm sorry, and then I have 4 boxes, so I have 3 boundaries, plus 4 minus 1 divided by 4 minus 1. That's where I'm putting my boundaries. Okay, and that's how many answers I have. How many possible ways of doing it? Okay, 4 plus 4 minus 1 is 7. Choose 3. And you have to figure that out. Okay, great. Next. Okay, number 13. Sorry. Number 13. sorry, I did 7, I have to do 9. 9 is a pain in the neck, I'm just going to write it up. Okay, we're in section 5.3. 9b is just using the binomial coefficient. So it goes as follows: x minus y to the 6. Use the binomial coefficient here. Those are the numbers beforehand. Notice whenever y is an even power, it's plus. 4 plus, 2 plus, plus. There's y to the 0, so it's plus. Whenever y is to an odd power, it's a minus beforehand, because minus y to the odd power is a minus. So there's going to be a minus here and a minus here. Okay? This becomes 6. I'm sorry, this becomes 1, 6. 6 choose 2 is 15. 6 choose 3 is 20. 6 choose 4 is 15. 6, 1. Okay? And I wrote up the final answer there. 14a is going through this, putting the, in the class I said you have n plus k minus 1 dashes, okay? And if you have k boxes, to split k boxes, you need k minus 1, I call them boundaries or separators, okay? So what they want you to do in 14 is go from writing it as zeros and ones to putting it into boxes, going from putting it in boxes to going to zeros and ones. So I gave you the answers for the first 2 of them. It's just way too simple. So let's do number 17. For how many integers between 1,000 and 9,999, key point, 4-digit integers, sorry my hands are so dirty, 4-digit integers, it's from this whiteboard, 4-digit integers, is the sum of digits exactly 9? Okay, now the main point is as follows. You cannot have a 0 here. So you have to put 1 over there. So you have 9 of these numbers. You have to think of them in 9, and you want to put them in a 4-digit thing. We did this at the end of the chapter. So you have a 4-digit number. This one, you're going to put some of those values into these 4-digit numbers. This one definitely can't be a 0. So you put 1 in there. What's left? I have 9 digits. I put 1 over there. I have 8 left. And I want to put them into 4 different boxes. So I have 3 boundaries. 8 minus 4, 8 plus 4, sorry. 8 plus 4 minus 1. I have the 3 boundaries, and we have that. That's the answer to the question. Okay? Anyways, I'm sorry, this is a little bit quick, but again, I'm here to show you how to do it if you're stuck, but you're supposed to be able to do it on your own. Okay? So I hope my hints helped you.